Welcome. This is the third installment of our 4.4 homework problems. We're going to go from number 28 through number 38, which will take us through the first page. This will take us through page 181 of the beginning of our homework assignment. Number 28, we are given y equals ln 10 to the x, and we are supposed to find the slope of this. So let's take a look. We've got a formula for when we have ln's, and it's a pretty good formula. We like this one. So we're going to work off of this, but we don't have ln of x here. We have ln of a function of x. dy dx is ln of 10 to the x wants to just be 1 on 10 to the x. However, we have to compensate for this not being just plain old x by taking the inside derivative. And the inside derivative is a non-e number to a power, such as a. E to the x's derivative is just e to the x, but we compensate when it's not e by multiplying by ln of our base. So I now need to find the derivative of 10 to the x, like this. That wants to be 10 to the x. We compensate because it's not e with ln of 10, and then we take its inside derivative, but its inside derivative is just x. So 10 to the x cancels, and I get, believe it or not, dy dx is a constant ln 10. Number 30. Number 30, we got some words in this one. It says a line with slope m passes through the origin. Oh, I'm sorry, that's 32. Number 30. At what point on the graph y equals 2e to the x minus 1, at what point on the graph of that function is the tangent perpendicular to y equals negative 3x plus 2? Well, lines are perpendicular when their slopes are reciprocal, so this one means we want the slope to be the opposite reciprocal 1/3. So I'm going to find slope formula and set it equal to 1/3. So I get dy dx is, now, 2e to the x, as I often say and will continue to say, a constant times a function survives the differentiation process. So this is going to be 2 times derivative of e to the x. Hopefully we're calling that one because that's our favorite derivative out there. 2e to the x. The derivative of e to the x is e to the x. dx dx, but dx dx is 1, so it's just e to the x. I want that 2e to the x to be equal to 1/3, or I want e to the x to be equal to 1/6. To eliminate e to the x and just get x, I take ln of both sides, because I would say ln, that's base e. So this is the exponent that turns base e into e to the x. X does. X equals ln 1/6. So I'm going to put 1/6 back into my function because I know the equation of my line is going to have a slope of 1/3. I want the equation of the tangent. Again, I'm going to read the whole directions again. At what point on the graph, that's what I'm looking for, is the tangent line perpendicular. So at what point on the graph, the point is ln 1/6 something. What would the y coordinate be? 2e to the ln 1/6 minus 1, the y coordinate. Well, if ln 1/6 is the exponent that turns e into 1/6, and I've got e raised to the exponent that turns e into 1/6, this is 1/6. So I get 2 times 1/6 minus 1, or 2/6, 1/3 minus 1. I get negative 2/3. And that is it. Now, the back of the book has that as an approximation. So you'll see here we've got ln 1/6 is negative 1.792. We get approximately negative 1.7 .692, and this one would, if we round to 3 decimals as we do on AP test, we get negative .667. I kind of like the exact answer. Okay, number 32. Number 32, compared to all the problems we've done up till now, definitely raises the ante a little bit. It says, a line with slope m passes through the origin and is tangent to y equals ln x on 3. Now, ln x on 3. ln x on 3 is going to look something like this. I know x can't be 0. ln x on 3. So we're talking about a point right here. This is y equals ln x on 3. Okay. It says that line passes through the origin, so I know it's of the variety y equals mx. And I'm going to say there's a point on here. Let's call this our point of tangency. This must be a ln a on 3. So the slope of the line from 0, 0 to this point, based on the linear, that is slope equals, it rises ln a on 3 as it runs a. All right, let's find slope formula of this guy. dy dx would be the derivative of ln x on 3 is 1 on x on 3. Do we need to take a look at that one again? Maybe we should take a look at that one again. It's 1 on times the derivative of the inside function being x on 3, so the derivative of x on 3 is 1/3, and interestingly we get 1 over 3's cancel in the denominator, 1 on x. So this has a slope of 1 on x, but we want that slope at x equals a that instant, and at x equals a that would be 1 on a. But what do I know about the slope of the curve and the slope of the tangent line at that instance? I know that 1 on a is equal to ln a on 3 on a, or 1 equals ln a on 3. I just need to solve that for a. Well, if I take both sides and take e to the on both sides, I get e to the first e equals e to the exponent that would turn e into a to the 3. This is a on 3, so I get a equals 3e. So let's just make sure we answer the question again. A line with slope m passes through the origin and is tangent to y equals ln x to the 3. What is the value of the slope? We get slope equals, that's a on 3 equals e to the first. Let's go back and fill that into our slope formula. Slope formula for a would be slope equals ln a to the third. A is 3e, so that would be ln 3e on 3 all on 3ea. So our slope is ln e 1 on 3e. Sneaky little problem. Back of the book has the answer as 1 on 3e to the negative first. So, man, that definitely raises the bar compared to some of the mechanical problems we've been doing. But that is a pretty famous type of AP calc problem. So one that we're going to need some practice on. I highly encourage you to take that now, especially if you were just looking this one up, and try number 31. Number 31, same problem, answer in the back of the book. Expect you to give that one a try if you didn't follow it, or even if you did follow this. Practice would do you a world of good right now. Okay, let's jump to number 34. Number 34, all of a sudden we just jump back into mechanics. It just says find dy dx. Number 34, surely there must be something to it. It says y equals x to the 1 plus root 2. And we may build a big monument to this 1 plus root 2. But bottom line is 1 plus root 2 is just a number. So they're trying to throw us off here. If this was x to the 7th, dy dx, man, that is right in our wheelhouse. 7x to the 6th. What do? I take the exponent, 1 plus root 2, I put it down in front, I reduce the exponent by 1, 1 plus root 2 minus 1 is just root 2. Could it be that simple? It is that simple. Number 36, y equals x to the 1 minus e. So we got x to the 1 minus e, but 1 minus e is just a number. Don't get hung up and think this thing's if ever there was a chance to make a mountain out of a molehill, this thing isn't even hardly a molehill. This is like an anthill. Nothing to this. This is x to a number. If this was x to the 12th, it would be 12x to the 11th. If it was x to the nth, it would be n times x to the n minus 1. If it's x to the 1 minus e, the derivative is 1 minus e, all of it, x to the subtract 1 from this. Well, 1 minus e minus 1 is just negative e. We might write this as 1 minus e on x to the e. That might be what we do. That the back of the book doesn't even do this. Nothing to it. Number 38. Kind of a nice twist after 32. They give us a couple of softballs. We get f of x is ln 2x plus 2. And we are asked to find f prime x and state the domain. So we want f prime of x and its domain. Well, right now I know the domain of this function. The domain of this function, 2x plus 2, has to be bigger than 0. Therefore, x has to be bigger than, subtract 2, divide 2, negative 1. And a logarithm should be differentiable any other place on the curve. Now, maybe we look for something special to happen when we find the derivative of this, but this logarithm, we know at negative 1 we've got an asymptote. Now, I don't know exactly where this curve fits, but I know it's getting bigger as x is getting bigger. It must look something along the lines of this, and it's differentiable at any point. So I expect that to be our domain. So domain I expect to be negative 1 not including up to infinity. Unless something weird happens along the way, that's what I'm going with. So let's find the derivative. F prime of x equals ln. Do we need to see it again, or are we starting to get it? Ln, derivative of ln wants to be 1 on the function. So this, or 1 on the Beatty function, 1 on the inside. So this wants to be 1 on 2x plus 2 times the inside derivative, which is just 2. So that wants to be, those 2's reduce, 1 on x plus 1. F prime x. Now see, if I look at f prime x, it would say, hey, it's all, any value of x except for negative 1. But we can't do that because this graph only exists to the right of negative 1. So that's why we include that, where x is greater than negative 1. Oh, okay, I understand now. Because I can look at this and say, oh, well, the slope at negative 10 is negative 1/9. But the graph doesn't exist over there. So good thing to keep in mind when we have a graph that does not exist over the entire set of real numbers. Okay, I'm going to stop this set here, and we'll get this one linked up for you. And thanks for joining us. Again, reminder, let's go back and take a look at that problem number 31.